Alright, hi, this is class 8. We've gone over this video, and now we're going to start talking about what we're actually doing in class today. There we go. I'm on. Great. So we're right here. A few things just to go over. I'm going to briefly go over lab 1. I realize you've seen it a bunch of times, but just to clear things up. So people with their M&M's projects, they were cool. I liked reading through them. Just if you're like curious what normally happens, because people are finding all sorts of random stuff. Briefly, M&Ms melt in response to temperature. So they melt in response to heat. All right. So if you're trying to do your test, right, and you're saying, okay, is it temperature? Is it heat that's melting them? And you put one M&M in your mouth and you suck on it, and you have your control M&M just chilling on the desk. Is something wrong with that setup? Something is wrong with the setup. What is wrong with that setup? So I've got one M&M chilling on the desk, and I made extra special sure it was the same color of M&M, and now I put the other M&M in my mouth, and this one melts. So I can assume it's obviously heat. Well, I'm getting head shaken. Why? Why can't it be like heat at that point? It is heat, but why can't I know that just on that test? Yeah, Zach. Yeah. There totally could be other possible things acting on it. So if I want to see if it's the heat thing, I need to check that, right? I need to try a little jar of my warm spit versus a little jar of my cold spit, and put the M&Ms in and see what happens. Or I need to, if I think it's the water, I need to try maybe my mouth, but one of them is wrapped up in the plastic wrap so it doesn't get wet, right? I need to test what I'm actually looking for. You okay with that? So if you're testing heat, you need all the situations to be the same except for the heat. If you're testing moisture, all the same except for the moisture, right? Just for what it's worth there. And then for quizzes, people are doing really well. This quiz, it was odd. I think I maybe sent you an email about this. People either did, okay, there are a few people who got like 8s, but most people either like got it all or kind of struggled, which is fine. Just, I now feel like we should go over a couple things. Take out a piece of paper, and you're not trying this. You're still not trying this. This is just for your own personal practice. Take out a piece of paper, draw 2 water molecules, and have a hydrogen bond with each other, okay? And then you draw the picture, draw it big enough that you can then show your socially distanced buddy, and you'll see if your pictures look the same. Online people, feel free to follow along. You've had a chance to draw it? Show your neighbor? Do they look similar? Okay. Looks like at least one group, and this is fine. This is why we're doing it. Doesn't look like they match, which is okay. So help me out. I want to draw water, I want to draw 2 water molecules. How do I draw a water molecule? 2 H's and an oxygen. Okay, I'll put that one over here. Great. I want to draw a hydrogen bond. Haven't I already done that right here? No, people are shaking their heads. Why not? I just happened. It's a bond. It's a hydrogen bond is this hydrogen. Well, a hydrogen with something that's not in the same molecule. Okay. Cool. Fine. But okay, I need to do hydrogen. I need to do hydrogen bonding. How about these lights? Kind of weird me out a little bit. What about something like this? And these guys can be little buddies. No, heads shaking. Why not? Yeah, they've got the same electric negativity. They've got the same like partial positive charge. That's not going to work. Okay. What about? Ooh. This. This is cool looking, right? Am I getting better or worse? Worse, right? Because there's made worse. Okay. You're not going to like the oxygens being next to each other either. Fine. Okay. How do I do it then? What molecules need to? Sorry. What atoms of the molecules needs to pair up? Here? The rest of the class? Is she right? Yeah. The hydrogen bond's here. Okay? We're good? Sweet. I feel like it is not my only life goal, but one of my life goals is to get people to draw water like this and to draw hydrogen bonds like this. Like, I don't know why, but I will have achieved something if this can happen. Alright. Are we feeling comfortable with this? Great. Okay, now on to the actual part that you showed up for. We're talking about lipids today. So, lipids, as your book helpfully describes them, are a diverse group of hydrophobic molecules, which is just a fancy way of saying there's lots of different types of these things, and they're scared of water. They're hydrophobic, okay? They're not scared of water because they had a traumatic early childhood experience with a pool. No. They're scared of water because they don't have these polar covalent bonds that, say, water does. So they don't mix well with water at all. All right? So lots of different types of lipids, but regardless of type of lipid, it's not going to play well with water. There's going to be a bunch of carbon and a bunch of hydrogen on this stuff, and that's what actually sets this up. There are three really important types of lipids for biology: fats, phospholipids, and steroids. We'll see all of them. I was going to bring this in, but okay, it's just me or these lights doing weird things. Why do they do weird things?
I don't know.
Okay, cool. I'll just carry on. Can you see the board all right? It's okay? Great. If all the lights go out, we're just going to move on, I guess. I was going to bring this in as a glass of water and oil and be like, ooh. But I thought you'd think I was just being dumb. So, pictures. When you mix water and oil, they don't mix well, right? Is it just because oil is less dense and, like, goes to the top? No, right? Because, like, I know this might depend on what type of kindergarten you were, but have you ever thrown a crayon in water? Right? Does it float? It doesn't, right? It kind of plops to the bottom. But it doesn't dissolve either. It doesn't mix well with even though it's more dense, even though it sinks, it also doesn't mix well. Any of these oily kind of things, more dense, less dense, they're not mixing well with water. And there are reasons for this. The first type we're going to talk about is fats. All right, so fats are going to be a fatty acid, which is this long, basically carbon-hydrogen chain, and something called glycerol. The picture looks like this. We've got, sorry, normally I'd point, but I'm going to be over here just to have the audio be better. Long fatty acid chain. Long fatty acid chain, long fatty acid chain. Carbon is not oxygen. Carbon's not greedy for electrons. So this bond right here is pretty much nonpolar. It's just pretty chill. This bond's pretty much nonpolar. This bond, these are all, okay, that's gonna freak me out. Sorry. All pretty much nonpolar, right? Um, over here, we have what's back up here as, this glycerol. It's 3-carbon alcohol that then holds all these 3 fatty acids, okay? Because these are all basically just non-polar covalent bonds, it doesn't hang out well with water. This hydrogen doesn't want hydrogen bond with oxygen. It's happy where it's at. If oxygen on a water molecule comes over here and is like, hey, I want a hydrogen bond with somebody, all of these are good. They don't want a hydrogen bond. Similarly, if the hydrogen with partial positive charge on it from water comes over here, nobody wants to bind with it either, right? So these ones so this molecule hangs out with other fats and excludes water, and water excludes this fat. Does that make sense? This molecule, you might notice, is big. It's a big molecule, right? This is all one molecule. It's not a polymer, because you don't get this molecule and attach another one, attach another one, attach another one in a molecule. You don't string them together. You do clump them together, though. These are all going to clump together because they're hiding from water together. They'll be next to each other, but they're not a true polymer. Can we find that? The flavors of these can change a little bit too. So this fatty acid chain, like all 3 fatty acid chains might be the same length. You might have one that's shorter, you might have this one that's shorter, but those 2 are a little bit longer. You might have slightly longer, slightly shorter. Different versions of the same thing. Okay, you can have different types of fats, but they're following the same basic rule. So far, so good? Have you heard about saturated versus unsaturated fats? Yeah? Briefly, something like bacon grease is moving towards being saturated, right? And something like olive oil is unsaturated. Which one's supposed to be better for you? Unsaturated, right? Think about what this means, though. So, not talking about oil, but like if you have a sponge that's saturated, is it full of water or empty of water? Like, full, right? Okay, if something's saturated, you can saturate. Okay, it's full, all right? Let's look at this little picture here. Every carbon has as many hydrogens as it possibly can. Is that true? Great. Before I get into this, are we okay with, this little zigzag pattern here? This zigzag pattern here is showing there's a carbon at every bend, and there's hydrogens around there. People just got tired of drawing every single hydrogen. You okay with the picture being the same? Okay. So, something like butter, it's a fat. Every single carbon has as many hydrogens as it can, all right? The shape of this thing, of this fat, is pretty much flat, right? If you had a whole box of these, could you stack them easily on a shelf? They'd stack pretty well. Anybody here ever worked at a grocery store? No? Can you imagine working at a grocery store? Some things are easier to stack than others, right? Like boxes of pasta, easy. Cabbages, less easy, right? Cabbages are okay, but like weird shaped things are trickier. Fair enough? Okay, so saturated fats are full of hydrogen, right? Every place they can have hydrogen, they've got this hydrogen. Unsaturated fats aren't full of hydrogen, meaning they don't have their bonds aren't saturated. So right here, you have carbon, carbon, but instead of having an extra hydrogen in each, They got rid of that hydrogen and have a double bond. Carbon's following all the rules for how many bonds it can have, right? It's fine. But it has that double bond, which makes a bend in this stuff. So now, this fat has a kink in it. You trying to stack a bunch of these together on your shelf? Do they stack as tightly? They don't, right? They don't fit quite so well, right? Like if you try and stack binders in, like they might all be the same shape, but they don't fit well because then they don't jam together quite so well. Unsaturated fats are a little, well, typically they're not as hard. They're like at room temperature, they're often liquid, right? Something like peanut oil, canola oil, whereas something like bacon grease or tallow, this stuff's solid. It just packs better. We're okay with this? For now, this is just like interesting tidbit to know. Later in cell molecular biology, it becomes important of like how does the molecule behave, and how does that behavior impact what, say, the cell membrane's doing? Okay, but we're good for now. Sweet. And then this is mostly for online folks, just words to describe this. Fatty acids can have different numbers of carbons. They can be different lengths on their chains. They can have different amounts of double bonds. If you have a double bond, you're not saturated. So double bonds are going to be unsaturated. No double bonds are going to be saturated. Okay, on to the next type, phospholipids. These guys we're going to talk about today, and then in about, I think, 2 weeks, a week, sometime, we're going to talk about the cellular membrane, and these guys show up all the time. It's a weird molecule, okay? The phospholipid, it's an odd molecule because it's got some weird things going on. So this right here, it's got a fatty acid tail. Well, it has two fatty acid tails. Well, right here. So it's got this, for all the world, this tail should look very similar to the fatty acid chain that's in regular fat. So something like this, right? Similar? Right, so it's got this fatty acid chain. Does that want to hang out with water? No, right? Absolutely not. Hydrophobic, does not want to hang out with water. Absolutely not. Nope. But look up here at this head region, this part right here. This is a phosphate group. Note the charge there. This would love to hang out with water, right? Nothing would make it happier than to hang out with water. And there's also, this also happens to be charged up here. It would be, the head is hydrophilic. It wants to be in water. The tail is hydrophobic, but they're connected. So who wins? Right? This is one of those, like, will we have to compromise situations, right? Yeah. So, wait, let's, I'm gonna try turning these back on, but I don't think so. Okay, I'm right here on the board. Can you all see this box? Okay, it's because online people can see this box. Okay, so phospholipids. So the phosphate group and the lipid part, right? Would love water, does not like water, right? So, yeah. How do you set this up so that everybody's happy? If you're in, say, an aqueous environment, you threw a bunch of these things, a bunch of these phospholipids in water. Phospholipids are going to bunch up so they're happy, right? They can do it in two main ways. The first one's perhaps most obvious. I'll show it to you, and then we're going to ignore it. I need these to be smaller. It's something like this. Is that okay with my notation? The circle represents the phosphate group. This is the lipid part. So one way they can bunch up is this. It's called a missile. Not like the bomb kind of missile, but anyways. Where now all these phosphate heads are touching water. They're happy. And all the hydrophobic tails are hanging out with each other. They're happy too. We're good? Yeah. So far so good? The other way, and this is more biologically relevant to us, is this, where you line them up like this. And then you have this group like that. So you've got water out here. These phosphate heads are happy. You've got water out here. These phosphate heads are happy. These lipid tails are next to each other, and this excludes water. So they're happy because they're with their other lipid buddies. Water's out here, and this is pretty stable. So far, so good? It's called the phospholipid bilayer. It sets up cell membranes, like all cell membranes. They'll have other things in them, in the bag that holds the cell together. There'll be other stuff. But this is most of it. And it's odd to think of the like structural support that holds your bags of cells together being basically olive oil, but it is. All right. Why is this picture terrible? If so, this one's good. Don't tell me why this is terrible about my drawing skills. None of that. Why is this picture terrible? We have something like this. Isn't that basically the same picture? This one's really bad. Why is this really bad? Yeah, Jesse said the hydrophobic tails are outside, right? So these ones are hanging off one. That does not. These are unhappy. These are unhappy. Everything is super unstable, and they don't do this. They do not do this. They do this. These ones are jammed next to each other by mutual attractions and repulsions of being afraid of water or liking water. This is not officially a polymer, okay? They're next to each other. They're forming up this phospholipid bilayer. That still doesn't count as a polymer. All right? Because this molecule is still distinct from this molecule. Anything here? I deeply feel like I should make that be some sort of quiz question. I'm going to leave it on because why not? Comfortable with phospholipids? We'll see more of them later. It's going to be good. Yes. I'm trying really hard to have what I say and the notes link up, which is throwing me off slightly. So here's that picture that we tried to draw on the board, especially for online people. We're trying to draw. All right. So we've had fats, right? Fats are going to be used mostly for lots of things, but you're going to use them for energy in the cell, right, or to store things, right? Phospholipids are going to be holding on, are going to be making these membranes. The last class that we're going to care about are things called steroids. So help me out. True, false. All steroids are bad, and the only reason you'd ever use a steroid is if you're a baseball player and really, really want to win and think you can do it without getting caught. You're shaking your head. They're all sorts of steroids, right? Steroids aren't categorically bad. No, they're an important thing, and you need them. So steroids are just describing lipids that have this 4-carbon ring structure. All right. Steroids are really important. They're going to do a bunch of things. They're going to help. they're going to help for a bunch of physiological processes. They're going to help signal a number of things. For what we care about, they look like this, more or less. They've got this 4-carbon ring. There can be variations here. They're a lipid. You need them. Cholesterol is a really important version. It's a steroid. You really need it for your cell membranes. And just know it's a lipid when it comes up later. All right? There are a number of very important things it does, but for now it's just, yep, steroids, they exist. They're lipids. They've got this 4-carbon ring structure, and they're important. Questions, concerns? Okay. The last 2 things we have to do for class are briefly look at what's coming up next for Friday. And then at the end, I want to do a review of what we talked about last class. All right? So, everyone's feeling comfortable with lipids? 3 types. Mostly nonpolar. Great. Okay. Cool. Proteins. Proteins, we're going to spend all day Friday talking, well, not all day, all class Friday talking about proteins. They're amazing. There were those 4 types of large biological molecules. We've had lipids, right? We've seen those. We saw carbohydrates, nucleic acids. Proteins do so much. So if you dry out a cell, you're ignoring the water. Dry out a cell, about half of how much a cell weighs is protein. So yes, the lipids are making the membrane, sure. The nucleic acid is holding information, great. Carbohydrates are doing some structural support and some energy stuff, also great. I realize these are oversimplifications, but big categories. Proteins are basically doing everything else. They're really carrying the weight of things. You can't, they're absolutely not plastic, okay, they're not made of plastic, but you can kind of, if you think of them more or less as plastic, being like, yeah, you can have plastic that's saran wrap, you can have plastic that's really hard, you can have plastic that is used in building, you can have plastic that you can like bend and do stuff with, right? It can be whatever shape you want, it can be whatever color you want, it can be whatever size you want, right? That's where we kind of are with proteins. They can do tons of stuff. So we'll see lots of these tons of stuff. They can be enzymes, right? So if you're gonna like digest food, proteins will help speed up that reaction. This is important. So they're gonna help. They're gonna be enzymes sometimes. Proteins can be things like antibodies, which I realize are becoming more and more on people's minds these days, right? They're made of proteins. If you want to store amino acids, you're using a protein to do this, right? If you need to, say, move stuff around the body, or it could be a tree too, but if you want to move stuff around, you're going to often use a transport protein. So like, you want to move oxygen around your body? Great. You need hemoglobin as like a carrier of oxygen. That's a protein. So far so good? But wait, they do more stuff too. They're gonna do hormones. You got hormonal proteins, right? So like insulin, that's a protein. It's important for blood sugar regulation. Is everyone feeling like protein's doing a lot? Carrying a lot of the weight here of the cell? Yeah. Oh, and now it just lit. Okay. Proteins are also going to do things like receptors. So for instance, if a bug crawls on you or you feel something, there can be receptors to the changes that occur. Those receptors are going to be proteins. And as those change or let in different chemicals, they'll send a signal. Yeah? The one that's perhaps most common or most intuitive is muscles, mostly protein. Right? You're okay with the idea? Muscle is mostly protein, and that can contract, right? It can move. It's important. You can also have movement based on protein that's like a lot of people you've seen your little microorganisms that have like flagella on them, right? Those are going to be moved via proteins to flap along. People have been doing the lab so far. It's kind of cool. Anybody actually find an amoeba yet? Oh. Say what? The dead ones. Do you find a live one? Oh man. Drat. Sorry. Dead ones are cool. If you can find a live one, it takes like half an hour to find one usually. But it's cool. Because you can be like, yeah, they're cool. If you keep one as a pet, you feel like, this is my pet amoeba. I don't know what a good name for pet amoeba would be. Amy? I don't know. Okay. Sorry. Sorry. Jesse's like, yeah, okay. If you have a better suggestion, feel free. It's probably what I'm going to give my kids as pets. My daughter is about 2. She deeply, deeply loves puppies, at least the idea of puppies, right? Like, she has a stuffed puppy, and she sees them, and she waves. I don't know how she feels about, like, real live dogs, but she likes the concept so much. Anyways. She might get an amoeba for her birthday. Structural proteins are going to do support. Proteins can also be really strong, right? So things like fingernails, horns, yeah, like spider webs. Those are made of proteins. They can be structurally strong. Concerns, questions were solved that protein just shows up a bunch is important. Great. On Friday, we'll talk about why it shows up and is important all the time. With that, I really like people taking quizzes in class because I like that they can draw and do all sorts of things. That being said, in these unprecedented times, I think it makes more sense to have you just all do the quizzes online. Is that true? Because then everybody takes the exact same quiz, the exact same timelets? Okay. I'll send the email out to the class about that. But so on Friday, you'll have a quiz, but you'll have a quiz not in class. Alright? But what we do have in class right now is a brief review. That's not what I want. Go back. I would like to play this one. Great. Does everybody know what we're doing with this? Anybody not here on Monday? We can go through this. I'll get you theirs on Friday. It's Adam, right?
Yeah.
Great. And online people, I'll post the questions we did the review, but this is it for class. Sorry. Takes me a second to stop everything. Stop recording.